basically done with brute force algorithms, or everything that I intended to cover. If you take a look at the lecture notes, like the semi-book that we have, then you'll find that there are a lot more algorithms that are covered in there. Generalized combinatorial generation, right? Repetition, permutations with repetition, combinations with repetition, and stuff like that. But it won't necessarily be used directly. So I was going to move on to the next part of this course, which is, which is divide and conquer algorithms. Now, you've seen divide and conquer algorithms before, I'm sure. Merge sort, quick sort, binary search, and we might take a look and revisit some of those over and again. But we're going to start simple. We're going to start at the core of the general divide and conquer strategy, right? And the idea behind that divide and conquer strategy is, is it Sun Tzu or so? I forget who it is. The Art of War, right? Where the best way to defeat an enemy is to divide their forces and then overwhelm each part of it with your forces so that you divide and you conquer, right? And I'm sure that it's not, modern-wise, we give credit to Sun Tzu or whoever it was, but I'm sure that it's something that has been, part of humanity for millennia, right? But basically, you have to first divide a problem into smaller parts until the problem is easily or trivially solved, right? This is often referred to as a base case. And for that reason, divide and conquer strategies, divide and conquer algorithms, are generally presented as a recursive solution. So in general, recursion is bad because you are paying for the recursion, and when you could, always simulate the recursion iteratively. But it is easy to think about these divide and conquer strategies from a recursive point of view, where we take the problem and we break it up into multiple pieces, and then we go ahead and make a recursive call on this piece and a recursive call on this piece until we get down to that base case, where we no longer do any recursion. Instead, we just directly solve the problem, right? But on our way back up from the recursion, you may then need to combine sub-solutions to produce a larger solution, right, to the actual problem. So that's not part of the divide and conquer mantra, right? The divide and then you conquer, that's the base case. Well, how do you build a larger solution up from these smaller solutions that you created? And that's part of the conquer as well, right? You have to figure out how to do that on your way back up from the recursion, right? And again, it's usually presented as a recursive solution, but it doesn't have to be, right? When I present binary search, right, we think of it recursively, and we can even present a recursive version of binary search, but in actual implementations, you don't do that. You do the divide and conquer using an iterative while loop so that you're not paying for that recursion, right? But otherwise, it's well suited for general approaches, especially in parallel computing or distributed computing. Right? Parallel computing, where you've got a task that you want to farm out to multiple processors, right? The vast majority of processors now have multiple cores. And if you can divide a problem into multiple parts, then you can take this part and put it on one core, take this part and put it on another core, right? And then you can do it in parallel. Or a distributed computing, where you're taking it and you're putting it on an entirely different computer, right? You divide this big problem into two parts, farm it out to that computer over there, farm that one out to that computer over there, or split it up even further. And so it's a well-suited strategy for those kinds of things. You might have seen something like MapReduce, right? Where you are reducing the problem and then you're mapping it back. That's a divide and conquer approach, right? Searching and sorting, right? In other words, like saying binary search, right? Quick sort, merge sort. Those are all divide and conquer kind of strategies that hopefully you've seen before. And then, of course, generally, you can think of these things in terms of tournaments, right? tournament style strategies. You do this all the time without even thinking about it. To demonstrate what I mean by that, let's go ahead and take a series of numbers here. I'm just going to steal my numbers from over here because I don't like generating random numbers. 5, 2, 9, 3, 2, 1, 1, 2, 3, 4, 5, 6, 8, and 7. There we go. So if you were back in grade school and you were given this as a busy work to get things done, how would you go about adding up all these numbers? Would you go and go serialized and just go from the top to the bottom? Okay, 5 plus 2, that's, all right, now in my head I'm going, okay, that's 7. And now plus 9, that's 16, 19, 20, 21, 22, that's 30, 37, all right? Is that how you generally do it? Or would you, if you wrote them out all like this, what would you end up doing? Match them. The first two, that's 7. 12, right? Now I'm not having to keep a running total in my head, right? 3, 15, right? All right, then what would you do? You'd add those, 19, 18, and then finally these two together. That's going to be 37, right? That's a tournament, right? How is it a tournament? Come on. Cut. Paste. And flip, right? What are you doing? You are dividing the problem, and if you will look at it from this direction, right, then you are dividing the problem and conquering it. That what we have here is a series of 8 numbers. Okay, well, I can't add up 8 numbers, but I can add up 2 numbers. So divide it into 2 lists, and now you've only got 4 numbers in this first one. Now divide that up into 2 lists, and you've only got 2 numbers in this first one. Now I know how to do this. Now I can add 2 numbers together. I could do that in my head. But adding 8 numbers up in my head, nope, that's not going to work. And the conquer phase is that once you have added those up, then you can continue adding 2 numbers to get another sum, to get another sum, and then finally add 2 numbers at the end to get one more sum. Right? That's just a general divide and conquer kind of approach, where you divide it into 2 lists, right, and then you recurse until you get down to the simplest form where you've only got one thing, and by definition that's sorted, merge sort. Or you've got 2 things, and well, I can add 2 things together, right, pretty easily. Okay. So let's go ahead and get some practice doing this in actual programming, in an actual programming language here. So I'm not going to type this out, but we will look at it. Come on, there we go. Now it's code highlighting. So as it suggests, I've got a linear iterative search here. Right? What is linear search? Given a list of elements, in this case, we're just going to give it a list of integers, right? We'll say A, right? Here's my test case down here. A is equal to 52932100947. And given that list, we're going to search for a key element, right? The key in this case, let's go ahead and say that it's 42. I want to search for 42. Okay? Is this big enough for everybody? All right. Let's go one more for the resolution on the live stream there. All right. So how does it work? Well, for each element in the range from 0 up to n minus 1, where n is the number of elements in it, we ask, is that equal to the key? And we return I here. The reason I'm doing this as a non-Pythonic kind of loop is because I don't want to just know that it's in there. I want to know at what index can it be found, right? In other words, if I did it more Pythonic, what would it look like? For x in the collection A, right? If x is equal to A, then return what? You found the needle in the haystack, but you don't know where the needle was to begin with, right? So I'm going to return the index at which I found it. And just like the documentation says here, returns an index at which the key exists, none if no such element. So if I get through the entire linear search here and I don't find it, I return none. Yeah, go ahead.
Is there a function for like the iterative for loop to like get the
That's what this is doing. Maybe Python.
The index.
element and index iteration list. Like a tuple or something like that. Iterate a list with indexes. Yeah, like that. There. You have to enumerate A though, it looks like. Gross. So let's rewrite it. Let's do it. Here's the element I and X in enumerate A. Right? And then you can ask the question, is X equal to your key? If so, return I. There, I've just rewrote it on the fly. Now let's make sure that this works. Right? So linear search iterative. I should expect what result here? Print. Let's do a formatted printing, right? So formatted string, and I found the key at index. There we go. Say what?
Does it keep going?
Hopefully not. Hopefully enumerate is not like an infinite loop there, right? Let's find out though. Python, and I'm using Python 3 here because of formatted string. So which Python? Python version. Okay, we are 3.10.6. Good. So Python divide and conquer. Found 42 at index none. Why? Because it's 42 in A? No. So you alter your print statement here, but let's go ahead and make sure that it actually works on something that is a valid search, 5. Found 5 at index 0. Now there are multiple 2's in here, so if I search for 2, what will this end up doing? Returning the first one that it finds, which is at index 1. Yep. 7. Let's make sure that it goes all the way to the end. It does. Found at index 9. So that tells you that there are 10 things in that list, right? Okay, that's the iterative way of doing it. Help me to define a divide and conquer approach to this recursively. Right? So let's go ahead and whiteboard it first of all. Right? So when you're thinking of recursion, you also need to be thinking inductively. Induction has the exact same structure as recursion. Your base case is the same base case, right? Your starting point. But with recursion, that's your ending point. That's where you do not do any more recursion. But they both have the same idea of, if you've got a statement pk, you want to show that this implies the same statement but for k plus 1, right? So in other words, given if you have this 1 implies 2 implies 3 implies 4 ... What you actually want to do is you want to jump into the middle of the induction, in the middle of the recursion, and think more generally. Right? So if I were just to think about this as an array or a list, right? Here's my array, index 0, 1, 2, ... up to n minus 1. And these are my elements, a naught, a1, a2, ... a sub n minus 1. That's not thinking inductively, because I am that's the entire array, right? I'm going to break this array up into multiple pieces. The first time I do this, I'm simply going to cut it in half, right? And here's the first half, 0 through, and let's call this m, right? And then m plus 1 through n minus 1. But that's just the first iteration of my induction, or of my recursion, right? I'm going to break this up further. I'm going to break this up into 2 sublists so that I have 4 sublists. Then I'm going to break that up further so that I have, how many? 8, etc. Oops, there, not that one. So I need to think about what happens at this generic level down here, k, right? Instead of thinking about the first one or the second one or the third one. So let's think about that. This is a subpart, right? Maybe there's something before this, maybe there's something after this. I don't know. I don't care because this is the subpart. How can I specify where this sublist is? I need to specify a left index and a right index. So I'm looking generically at a sub L through a sub R. Right? This is a sub L plus 1, a sub L plus 2, dot, 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 a sub R minus 1, dot, 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 that way. Okay? I don't know if that's divisible by 2. I don't, the only thing that I do know is that I've got L and R. Right? Now, what if L, let's think of some corner cases before, just as a, a whiteboarding thought experiment here, of what happens when L is equal to R. What kind of a sublist do I have then? L and R? That's how many things are in it? One thing, right? What about the other case where, say, L is greater than R? Right? Here the size is 1. What's the size here? Right? 0. Or negative 10, it could be, but either way, it's an empty list. Okay? All right, so those are probably going to be my subcases that I need to think about. Now, if I want to go further in the recursion, in other words, I want to go from p sub k implies k plus 1, I need to think about how to break this down even further. If I'm going to break this into 2 parts, where do I break it? Here's the middle. So how do I get that m given L and R? No? Think of them as numbers on the number line. L, R, M. So what? R minus L divided by 2. Okay. Let's try that with some specific values. 5 and, I don't know, 15. So that will be 10. 10 gives me the number of things here. But then 10 divided by 2 gives me 5, which is this index. Oh, okay, plus R. Right? Oh, sorry, plus L. You're right. Plus L. That'll work, and that's perfect. What's another way of saying that? Yeah. Not in Python. But yes, we do care about overflow. We also care about this division right here, especially in Python, because if I have, in a lot of languages, if I go 11 is divided by 2, what's the result? 5, not 5.5, because of integer truncation. Do we have integer truncation in Java, or in Python? No, because it magically becomes a floating point number, right? We don't worry about overflow. In fact, this is the better way of doing it. We would worry about overflow if we did this another way. L plus R all over 2. Why? That's the why. First of all, why is this valid? If you're on a number line and you want to get the thing in the middle between 2 numbers is its average, its mean. So if you add them together and you divide by 2, you get the average, the mean, right? This would be susceptible to overflow, underflow in most programming languages, right, that have a 32-bit 2's complement integer. But in any case, we don't need to worry about that, okay? But we will need to worry about the specifics in Python. So I want to break this down into 2 lists. Oops. 2 lists. I'm going to go from L up to, say, M, inclusive, and then M plus 1 up to R. Right? There's my first list, and there's my second list, okay? Now, I'm going to break that down until I get to that base case, where it's either empty, right? Empty, or it's of size 1. Right? Now remember, let's not lose the forest for the trees here. So what am I trying to do? I'm trying to search it, right? So if we get down to the case where we've got 1, and I've got X here, right? Empty, here, I'll go ahead and use the empty set for that instead. And I've got X for my element, right? Once I get down to 1, if X is equal to my key, then done. Right? I need to return the index at which I found it, which again was what? L is equal to R. Right? Otherwise, if I get down to empty, is there anything to check? There is no X to check against my key. So none. Right? Done. Right? So, help me write this. First of all, I'm going to define it as linear search recursive. I'm going to take A and the key as, because I still have to have the collection, I still have to have the key that I'm searching for. But what else am I going to take now?
Size?
I could take the size, but I've always got the size, right? The length of A is L and R, right? Remember, I have to keep track of what list do I have right here. I have the list from index L to R. And it's better if you call that left index, right index, or I'll just go ahead and go left and right. There we go. And same thing here. Returns on index at which the key is found. None if no such element. Okay. There is our documentation, right? Now, before I actually implement this, let's think about how we could actually call this down here. How do I get things started? Of course, I'm going to pass it the same list. I'm going to pass it the same key. But now, where do I start my indices? 0 and? N minus 1. In this case, it's going to be length of A minus 1, because I don't have an N here. Yeah.
Do we sort it before we do it?
If we sorted it, what could we do? Would we have to use a linear search? Not, in fact, if we sorted it, what other kind of search would we use? Binary search, right? All right, and we might revisit that later on. There is no built-in binary search to Python, because Python says if you want to do something like that, you should be using a dictionary instead, right? I didn't check everybody's code down to the minute level, but I think that everybody used a dictionary on their first assignment, right? Anybody not? Anybody use binary search? What? Okay, all right. You had to write your own probably, or get somebody else's implementation, because there is no implementation in Python. Python says use a dictionary. Don't do this. Okay, and that's not the only language like that. PHP is like that as well, because PHP does not have arrays. They have associative arrays, which are dictionaries. All right, so help me out here. What's the first thing I do in a recursive function? Base case, right? If L is equal to R, or left is equal to right, then I'm down to the base case where it's of size 1, right? And I check if the key is equal to the array in the left, right, which is equal to the array in the right, then I'll return left, right? Else, what do I return if I didn't, I got it down to one element. What do I return if it's not that element? None. Okay. All right. What's another case here? Go ahead.
Dictionaries are so good, why don't everybody use dictionaries?
Everybody does usually. I mean, if you have a choice, hash table. Well, that's what a dictionary is.
Is that how they build databases now?
Oh, databases would generally be B trees, because you have other considerations there. If it's like a NoSQL thing, then that's dictionaries, right? Because it's a key value pair, like MongoDB or something like that. But if you're talking about databases where you need the full ACID principles, right? Then you need to be searchable, right? You don't necessarily have the key. I want everything that matches this constraint, right? And now if that's metadata that has been sorted, then you can use binary search. Basically, what's binary search with B trees. We'll look at B trees later on in this course.
So dictionaries work best if you have a key.
A key valued pair. That's its bread and butter right there. Yep.
If you don't have a key.
Yep. Anything that's hashable. Anything that's a hash table. Yep. Okay. What's my other base case? Maybe I should have started out with that base case. If the left is greater than the right, then what can you say about the array? Empty array, empty list, empty sub list. So what should I return? None. Can you have a needle if you don't have a haystack? No. Right? All right. How do I do this? Else if in Python? Why? Because they don't have the else keyword, else if keyword, right? It's not really even a keyword in most languages. Otherwise, here, right? So we took care of the two base cases that we identified. When L and R, they go past each other, it's an empty list. You can't find it. When they're the same, that's the element that you should examine. If that's the element that you're looking for, then return left, or which is equal to right. Otherwise, return none. Now here is where we need to make sure that we're doing the recursion. Remember, we said L should be, or that the middle index should be what? Left plus right divided by 2. Bad math. Good numerator. But now think Python. 11 divided by 2. Am I going to be able to rely on integer truncation here? Nope. 11 divided by 2 becomes 5.5. Is 5.5 an index that you've ever heard of? Nope. So the best way to do integer truncation manually is with the math library. Right? Round it down. It's not even rounding it down, it's flooring it. There we go. I think you could also do this. Don't quote me on this, but I think you could do something like this. Is that right? Or integer or something? Yeah. But it's not really a typecast because there are no types in Python technically, right? You are giving it to a function. That function returns something that's guaranteed to be a whole number, right? I'll keep it as floor. And if I'm going to use the math library, I need to import math. Is it import math? I don't know, Python, math, floor. It certainly will, floor method. It's going to be guaranteed to return a, oh, there we go. Python 3 and up, it's guaranteed to return an int val, which is different from 2.0, which returns a float val. Why? Don't know. Yeah.
If you use a casting, is that what it's called?
Python integer cast. Don't go to W3C schools. But yes, I was right, it isn't. And so it works on strings too, apparently. This will be 2, so it does integer truncation.
Is it round?
Nope, I mean, look, 2.8, it'll end up being 2. It's truncation. So if you don't want to bring in a library, I guess, you could do this. Right? Arguably that's simpler, so great, right? M is now the middle index. M is the middle index with a favorability to the left, right? Because if it's 11 divided by 5, 5.5, it ends up being the left. Right? Now let's make our recursive calls, right? Search the left half and search the right half. How do I make a call that will search on the left half? A and key are unchanged. I'm still searching the same list for the same key, but my indices have changed now. What does it look like? It's going to be L, come on, wake up, L to M, and then the right one will be M plus 1 over to R. So, left, middle, M in this case, and linear search recursive A key M plus 1 right. Why don't we do M and M? My second favorite candy. Why don't we do M and M? Peanut butter, by the way. Say what? Can never have too much peanut butter. Why should I search the same M in both lists, right? If I've got if I've got a list of 4 and a list of 4, why should I overlap it and search this one element in both the left and the right. Right? So make sure that you're not doing redundant work. M plus 1. You could also go M minus 1 and then M on the other side, but that looks kind of weird. Right? Now, this is going to return a value. It's going to return an index at which you found it, or it's going to return none if no such element exists. So I need to capture those values, right? Index is going to be equal to this, and index is equal to this. I did the divide part, and I did most of the conquer part up here. But now I need to do the combine part, which is that part of the conquer. What do I do with those? First of all, I can't name them the same thing, so let's think about them as A and B, right? So here are two lists, right? And there's a result. There's a result A, and there's a result B. What do I do with them?
Return.
I could return, yeah, well, I got two results though, right? I found it at index B. I found it at index A.
Return B.
Okay. Return the first one at which you found it. So if you found it in the left half, do you need to search the right half? No. Did it say return all indices at which you found it? Return the rightmost index at which you found it? No, just return a index at which you found it. If index is not none, then I can return index. Not even bothering to search the left half, right? Don't bother with the right half. Excuse me, the right half. Return index. Otherwise, you may need to search the right half, and whether or not we find none or some, right? Some index, it's what we return. Right. Good? Let's find out if it works. Test. Well, let's search for something, first of all, that we know that it's not in there. I should expect this to be none. Excellent. And also, what do I know? It doesn't result in an infinite loop, right? Yay. At least on that input. Right? Let's go with negative 42. Right? Not that that would matter because it's still the same search. Right? Let's search for something that we know is in there, 5, at index 0. Let's search for something that we know is at the end, 7, at index 9. Excellent. Let's search for something that is somewhere in the middle, 1. I don't know what index that is. Help me out. Is that correct? 0, 1, 2, 3, 4, 5. Yes, I can count. Right. Let's search for something that we know is a duplicate. Which one will this end up returning? Probably the first one, yeah, because we have a bias here towards the left half. There we go, index 1. Are they? Okay. Yeah, it gets split up this way, but then it gets split up this way. And so you end up, okay, I end up not searching this stuff at all, right? That's called a quick search. It's a quick search only in that you might just get just as lucky as you would with a linear search, right? If you are searching for 42, you end up doing the same exact number of comparisons that you would with the iterative version, right? But you have the added benefit of paying for the recursion. So given these two solutions, which one is better? The non-recursive version, right? Well, I mean, look at the code. 20 lines over here versus just, 4 lines over here, right? So if you've resigned yourself to an unsorted array and you're not going to use hash tables, this is definitely the better solution versus this divide and conquer strategy. But at least it gave us some practice in developing these things. Right? It's not buying us in terms of anything in terms of efficiency, and I don't know. Maybe some people would argue that this is easier to understand, right? The divide and conquer. I don't know. Would anybody argue that after seeing the two different pieces of code in here? I wouldn't, right? But it is a general strategy, right? From an abstract point of view, it does make sense that if you divide stuff, it's easier to solve, right? And so from that perspective, maybe we did buy something there. All right, I'm going to go ahead and put this into the, oops, it's not C. What does it look like if it's C? Gross. It is Python. Python. Oh, exact same? All right, fine. Was there any color difference at all? Did you see? Okay. All right, go ahead.
What latex program do you use?
I'm not, this isn't LaTeX, this is Markdown. So if you want to see how the sausage is made, here's where I'm working from. This is Atom.io. This is on the right here. When I type something, hello, it automatically, say what?
Should we use this for?
You can use LaTeX within Markdown. X plus, or x squared is equal to y minus 2. And it will render like that. Right?
But it's in Markdown.
It's in Markdown, and that, when I push it to GitHub, you see it rendered. Because as of March this year, they finally, after 10 years, they added LaTeX support to their Markdown files on GitHub.
The Markdown itself supports.
No. I mean, it's not part of the standard. It's an extension. So, I mean, if you go and look at the notes that were posted, say, for brute force algorithms here, right? Prior to this last year, this nice LaTeX stuff would not have rendered, right? Instead, you would have seen the actual LaTeX code here. It would have looked more like the raw, something like, looks like this, right? There's the LaTeX, and it's not rendered, right? Markdown is a very nice markup language that is absolutely simple, bare bones. Unfortunately, way too many people have gotten the idea that we should add some stuff. We should add some stuff. You missed the whole damn point of Markdown, right? That it is simple. Keep it simple. Don't go mucking with it. The one thing I would disagree on though is it's LaTeX support, right? Embedding LaTeX support, oh, awesome.
So, but the homework's is written in LaTeX.
Yeah, the homework's in LaTeX. Oh, did I lose my color coding? All right, I just have to kick it in the butt maybe. There we go. All right, get it to re-render. Okay. All right, so now that we've gotten a little bit of practice doing that kind of divide and conquer strategy, in our last 10 minutes here, let's do another alternative. Right? The alternative that you can kind of see in some programming languages like, say, Lisp. List processing programming language. Has anybody taken 322 already, or is taking it? CSCE 322 programming languages? Okay. You might see Lisp in there, or you might see some other functional programming language, I don't know. But here's the idea. Suppose that I have an array, I don't know, 10, 20, 30. I don't want to go in order, 8, 2, and 7. It's really hard to think of numbers and not sort them in your head already, right? So here's the divide and conquer strategy that we're going to take. Instead of dividing it in two parts, what we'll do is we'll divide it into one part and then n minus 1 parts. So 0 and then 1 through n minus 1. And there are n minus 1 things over here. Right? That way, we've got one base case over here. Check it. If that's the thing that you're searching for, you're done, right? So if this thing, x is equal to key, done. Output 0, right? Otherwise, else, recurse on this part. And I'm not going to call it the right half because it's not half. It's one element versus n minus 1 of them. Fast forward into the middle of a recursion, right? Up to this point, you've got now, say, an index I, right? And this is I plus 1, I plus 2, dot, 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 down to n minus 1. I no longer have a left and a right index. Instead, I have I, right? And then the end. Now what I do is I check. check. Is my key equal to the array of I? If so, done. Return I. Otherwise, I'll recurse on I plus 1 through n minus 1. Yeah,
Why can't they just use a for loop?
exactly. Why can't they just use a for loop? Anybody know why? There are some programming languages without loops, and this is how you do it. Lisp, Scheme, Haskell? I'm not sure, right? But that's the recursive divide and conquer strategy mindset, right? Some languages do not have loops, and instead you have to use recursion like this. Right? What would that look like as far as code goes? So first of all, what's our base case? When do I get down to the end? When I is equal to n minus 1 for zero indexing, right? Then I'm done. If this is the thing I'm looking for, great, you found what you're looking for. Otherwise, return none. So in other words, you're simulating the for loop by doing recursion. What does that one look like? Copy, paste, version 2. Now here I'm not taking left and right, instead I'm taking that index variable. I'll call it index. Returns unindex at which the key is found, none if no such element. All right? So my base case is if index is equal to the length of A minus 1, then I'm down to where, or actually, let's go ahead and just go say length of A. All right, there we go. I've gone beyond the array, the list, and so I'll return none. That's the easiest way of taking care of that. Else, what do I need to do? Check the ith value, the indexed value. If array sub index is equal to the key that you're searching for, then return index. You're done. Stop the recursion, immediately go back up. Remember that you're going down in this recursion. If there are 10 elements, then your recursion is of depth 10 potentially. But if you get lucky and you find it at the third recursion, then stop. Don't go recurse anymore. Just simply go back up. Right? Else, here's where I call my recursive function. I don't change the list. I don't change the key. I change the index by going up +1. And that's it. Let's go ahead and do the same test suite over here with version 2. Right? Except that I don't pass it two things. Where do I start now? 0. Right? Python 42 found at index none. 5 found at index 0. 7 found at index none. Oops. Save it? I don't think I need to save it, do I? Oh no, what did we do wrong? Help me out. If it's gone 5, you've gone beyond it. Otherwise, if index is equal to the key, return index. Base of index, key index +1. I'm not sure. Say, let's try 4. Anybody online? Yes, I do have lectures on Git. Random internet person. Oh, okay, it's failing there. Oh, okay, let's search for 2. That might be a clue that we're failing in the very first. Yep, there we go. 5 was working though, right? So we get lucky in our base case, right? And I see it now. And I'm going to ask you guys, is there a linter for Python? No, so how do you detect bad things like, say, not returning a value? Right? What was I doing? Yeah, what was I doing? I was just calling the function and not doing anything. I was all, by default, if you don't have a return statement, what does a function do in Python? It returns none, which is why we were getting none all over the place. And here, this will probably work. 5 at index 0, what was it, 7? I'm pretty sure if 7 works, they'll all work, right? Anybody know of a linter? Linter for Python function that should return something. I think they're called hints, aren't they? And Python return value hint. Hints for function returning multiple values, but is that it? What was the okay. After the definition, you can do something like this. Int. There we go. And this should compile just fine, or should run just fine. But if I had forgotten that return statement, I'm glad we did this. Oh, come on, you can't detect that? None is not an integer. Import tuple, nope. All right, so Python hint not none. That it should not be none. Actually, no. How to hint optional arguments. Darn it. All right, anyway. This is called a hint. It means that you don't have return values because you don't have typing in Python, right? You can't say this function returns an integer. That function returns a double. But if that's something that you want to hint at, you can use something like this. Just like variable hints. Python variable hint. It's not a rule, it's just a hint. So, for example, let's say I need a variable, hi John, string, and this new name parameter is string. For parameters, fine, but what about actual numbers or actual variables? Name, string, maybe something like this. Let's try this, touch demo.py. All right, so number should be an integer, and I can set it equal to 10. Python demo. Okay, that works, but if I try to set it to foo, it should hint that that's wrong. No, okay. I can't get it to work. Somebody's going to have to check into that and see how you can enforce hints, or at least turn on like a warning system when something goes wrong. Right? But this would be like in an actual typed language where you have int x is equal to 10, right? It would be a compiler error if you attempt to do something like this. It's not going to be a compiler error in Python because Python's not compiled. Instead, it's just a hint. This thing should be an integer. If I ever set it to something that's not an integer, set off a warning or tell me or something like that, but I don't know how to turn it on. Right? And random internet folks that are watching us don't know how to either. All right. Anyway, oh, make sure I fix it. Return. There we go. Questions? Otherwise, please look that up. And if I forget to look it up, please somebody else look that up and tell me how that all works. All right. Okay. I'll see you on Friday. Remember that your homework 2 is due this Friday. That's just the 2 programs. So there's nothing to hand in through Canvas since there's no written part. If you it'll mark it as read and not handed in. If you want to hand in a dummy PDF because you just don't like seeing that, then go ahead. But otherwise, it'll just be graded like programs. Yeah.
Are we supposed to hand written stuff to
Canvas. Yeah. Yeah.
I handed written, but
I got yours. I got it.
we're not supposed to.
Yeah.